escape velocity.
That was a clip from the movie Hancock. Is it possible to throw a substance from Earth so that it's not coming back? Hi, this is Praveen. Today we are going to speak about the mathematical derivation of escape velocity. We are going to derive the expression for escape velocity. Before that, let's understand what is escape velocity. Escape velocity is the minimum velocity required for a substance to escape from the gravitational field of a planet. The minimum velocity required for a substance to escape from the gravitational field of a planet. That means, let's consider this is a planet of mass m and radius r. If I am throwing a substance with escape velocity, it will not come back to the planet, it will escape from it. We have to derive an expression for escape velocity. Let's have a smaller mass over here. Assume that we are having a smaller mass over here, and we have to throw it in such a way so that it is escaping from the gravitational force. What about the gravitational force? Is it a long range force or a short range force? Gravitational force is a long range force. Its range is up to infinity. Therefore, in order to escape from the gravitational force, this mass has to move up to infinity. Therefore, we are throwing the substance so that it is reaching up to infinity. In order to calculate the work done to throw the substance up to infinity, let's have two random points. We are having a point A over here, and this point A, it is at a distance x from the center of the planet. And I'm taking another point B over here. B is at a very small distance from A, therefore the distance from A to B, let me call it as dx. Dx is the small distance from A to B. In order to calculate the total work done to move the mass from surface to infinity, I am calculating the small work done in moving the mass from A to B. As we all know, the work's relation is F dot x. The small work done in moving the charge from A to B, it will be dw is equal to F dot dx. If I am applying a force in this direction itself, the force and distance, they are in the same direction. Therefore, I could write F parallel to dx. As a result, F dot dx will become F dx. Since cos theta will become cos 0 and cos 0's value is 1. Therefore, I could rewrite this expression as dw is equal to F dx. Clear? Then we have to find out the total work done from surface to infinity. In order to find out the total work done from surface to infinity, we have to integrate this dw. Integrating dw, we will get w. W is equal to integral of f dx. And in the integration, we have to substitute the limit. The mass is moved from surface to infinity. That means the limit we have to substitute from surface means it's from r distance to infinite distance. Therefore, the limit is from r to infinity. And what's f? F is gravitational force. In this case, the F value is gravitational force. We know the expression for gravitational force as F is equal to G capital M small m divided by, normally we are writing R square, but in this case I am writing X square because the distance that we are considering in this case is X. Therefore, F is equal to GMM divided by X square, where M is the mass of the planet, small m is the mass of the substance that we are throwing, and X is the distance. Therefore, I am substituting the value of F into that W. We will get W is equal to integral G capital M small m divided by X square into dx. Clear? And there should be limits given. It is from R to infinity. We have to take the constants out. Since G capital M small m, they are constants, we are taking G M M out. The remaining is integral r to infinity 1 by x square dx. Then, as we all know, integral of 1 by x square is minus 1 by x. Therefore, I am substituting the integral value over here. Then we will get w is equal to g capital M small m minus 1 by x. It should be written inside a square bracket within the limit r to infinity. Then we have to substitute upper limit minus lower limit. Upper limit minus lower limit means we have to write it like this: w is equal to g capital M small m minus 1 by infinity, minus of minus means plus 1 by r. Then what's 1 by infinity? 1 by infinity is 0. Therefore, the answer for work will be g capital M small m divided by r. But we require expression for escape velocity. Why did we find out work? It's because by finding out work and equating it with kinetic energy, we could find out the expression for escape velocity. That is, we are throwing the substance up to infinity. Therefore, the work done in this case is in the form of kinetic energy. I could write work done is in the form of kinetic energy. That means the work done is g capital M small m divided by r, and the expression for kinetic energy is half mv square, where small m is the mass of the substance. Then we could cancel this m, and we'll get v square is equal to 2gm by r, and v is equal to root of 2gm by r. This is the mathematical expression for escape velocity. V, escape velocity, capital G, gravitational constant, m, it is capital M, it is mass of the planet, r, it is radius of the planet. And from this expression, it is clear that escape velocity depends only on the mass of the planet and the radius of the planet. It's independent of the mass of the substance throwing. Clear? Then, as we all know, we are having an expression for acceleration due to gravity. That is, we know small g is equal to gm by r square. Therefore, we could write gm is equal to small g r square. And if I am substituting instead of gm, gr square, we will get another expression for escape velocity. That will be v is equal to root of 2 small g capital R square divided by r. That means v is equal to root of 2gr. This is another expression for escape velocity.